Okay, this question is about copper wire and copper compounds. Now you might think, okay, I know a little bit about copper compounds. I might know the ions. Now remember, it's paper 2, so it's going to be potentially about extracting copper or using copper in some way. Then it says copper is used to make electrical wires. Shows how copper electrical wire is insulated using an addition polymer. Now the fact that they are using the phrase addition polymer tells me we're going to be talking about polymers at some point. The addition polymer polybutene has the displayed structural formula. They've already given you that formula of the polymer. Polybutene is produced from the monomer butene. Now you've got to be thinking, right, do I know what butene looks like? Bute, okay, well that's got 4 carbons, so you've got to be thinking that's got 4 carbons, and the ene bit tells you there's going to be a double bond in there as well. Complete figure 2 to show the displayed formula of butene. Again, we've got the 4 carbons, well 1, 2, 3, 4, they've already drawn those for us, but we know there must be a double bond straight away. And then all we've got to do is put in the lines to show butene. Relatively straightforward. Copper can be obtained from recycling scrap copper metal. Well, for me, that recycling tells me I'm going to be doing my steps for how to recycle something. I'm going to potentially crush it, but then I'm definitely going to melt it, and then I'm going to reform it. That's really important. Whenever I see recycling, thinking about that. I might be talking about waste and why we recycle, and that's to do with energy as well as wastage. Okay, and it's getting my head in the right space. Suggest why polybutene insulation must be removed from scrap copper wire before the copper is recycled. Well, I've already gone for melting and reforming. I'm going to recycle it, which means if I am recycling my copper, I'm going to melt it, which means the polymer will also melt. Do I want my polymer? No, I don't. So I have to remove it first. Question 1.3. Describe how scrap copper metal can be recycled to make new copper water pipes. Well, this is why we do this beginning bit with recycling, because step 1 is we melt the copper wire, or the scrap copper wire, and step 2 we reform it or recast it or reshape it, and we reshape it into wires. Relatively straightforward, especially when we've already written that bit down, because it's getting our heads in the right place. Then suggest 2 reasons why recycling scrap copper is more sustainable. Again, sustainable is that word we're looking for, those keywords to jump out at us. Sustainable than extracting copper from copper ores. Okay, ores. I always think ore, I think the ground. And sustainable is linking to this bit, our waste and our energy. Well, why do we recycle it? Because then we have less waste, and then we use less energy. Relatively straightforward. Copper sulfate is a compound of copper. Copper sulfate solution contains copper 2 ions and sulfate ions. Now, for me, from a paper 2 point of view, and this is where it's important, I'm looking at copper 2 ions and sulfate ions and thinking, when do we talk about ions in paper 2? And there is a required practical of ion tests. So I'm thinking, right, ion tests. A solution can be added to copper sulfate solution to show the presence of copper 2 ions. Name the solution added, give the results of the test. 2 separate things. Name the solution and give the result. It always is laid out like this. So our solution, again, is sodium hydroxide. How do I know this? Well, the way I'm going to work out this is, I know it's a solution because they've told me that, but I've thought of ion tests and thought, what are my ion tests? They have told me it's a solution, which is why I thought sodium hydroxide solution. The other test is flame tests, and they haven't talked about using Bunsen burners, using flames of any sort. They talked about using a solution. Now, give the result of the test. Well, sodium hydroxide, the good thing about this is there's always going to be one word you're going to use, okay? You are going to use precipitate. That is the word, precipitate. or solid. I like precipitate because that is technically the right answer. And because it's copper, it's good because from our paper 1, we know copper sulfate is blue. Actually, copper 2 compounds tend to be blue, so we call it's a blue precipitate. Next one, describe one test. Okay, again, one is in bold, to show the presence of sulfate ions. Here we go, sulfate ions. They're asking for this. Give the result of the test. 2 marks, they give you the test, and they give you the result underneath. Now, we actually have 2 parts to this. We have hydrochloric acid. That's one part, that's one bit of, or part of the chemical we have to add, but it's also barium chloride, okay? I remember that because I think hydrochloric acid has a Cl and barium chloride has a Cl, so I'm going to use those 2 together, okay? And again, it's a test using solutions. I knew it, because it's using solutions, we're going to have a precipitate, and this time we're making barium sulfate, which is a white precipitate. Okay, it's a big question because it starts with all this information and it's easy to get lost in that. So, a student investigated the change in mass when hydrated cobalt chloride was heated. You might think, I don't have a clue what this is, but this is the crucial bit. They give you the word equation, and you've got to think, hydrated cobalt chloride is heated, and straight away I'm looking at this going, right, reversible reaction. I know it's a reversible reaction, and then it goes to anhydrous cobalt chloride plus water. Now you might not know about cobalt chloride, but this is where it's important. You're looking at hydrated and you're heating it, and you're driving water off at the end with anhydrous. For me, I'm thinking it's copper sulfate. Copper sulfate here, and this is copper sulfate. It's the same sort of thing is happening. It's the same practical or sort of demonstration you might have seen of blue copper sulfate reversibly turning into white copper sulfate plus water, and all of that. I think, why did we even show that? Why did we talk about it? Because it's thermal decomposition. Okay, so I'm looking at that. I'm not worrying about the method right now. I'm thinking, right, I've got thermal decomposition. That's what it was. This is the method. They then talk you through the method. They add some hydrated copper chloride, heat it, measure the mass, heat the test tube. Right, why do they measure the mass first and then heat the test tube? Well, if we look down at the table, with 0 heating time, this is how much was inside, 26.5 grams. However, they didn't measure the test tube without it. So it's really important that we look at this. Step 2 is measure the mass of the test tube and contents. Is this 26.5? After they've added 2 grams. So in reality, when we get to the question of determine the mass of the empty test tube, well, we know once we put stuff in, it's 26.5, and we know the very first step was adding 2 grams, so we need to take 2 off of that to equal 24.5, and that's where that comes from. Now, I've shown the information again. Explain why the mass of the test tube and contents decreased. Now, for me, if the mass is decreasing, I only ever think of one thing. Okay, if the mass increases, it's a gas coming in. If the mass decreases, it's gas escaping. So you think 2 marks, well, what do I need to say for 2 marks? If they give you a word equation, you need to use the word equation. So you've got to think, well, is that the gas or is that the gas? Is it 1 or is it 2? Well, water is more likely to be the gas, but we don't call it water when it's a gas. We call it water vapor. Okay, and some people call it steam, some people call it water as a gas. Water vapor is the gas, and it escapes. And if you notice, mass decreasing is gas escaping. We've got the gas escaping, and that's what it is. Okay. Now, suggest why the test tube and contents were heated until the mass didn't change. Again, suggest. It's a suggest question. It's saying what is happening when the mass doesn't change right at the end. These 2 points here. Why isn't the mass changing? Well, there's no reaction happening. If it stops changing, that means there's no more reaction. It's finished. Or the reaction has finished. Okay? The reaction is complete. And we see that a lot in chemistry, that complete reaction. How do we know when it's done? Okay, energy is taken in. Well, stop me right there. That's why I read this question. Because if energy is taken in, that tells me it must be an endothermic reaction. And then it has this question where 238 grams is heated until the mass doesn't change. And 88.1 kilojoules of energy is taken in. The student heated 2 grams until the mass didn't change. Calculate the energy taken in. And then this last statement, lots of people forget it, so I'm circling it. Give your answer to 3 significant figures. That's where you get that third mark from. Okay, so what we need to do is we do the 2 grams, that's what we've got, and we're going to divide it by the 238 grams, which they've given us as the example. Okay, and that is going to give us this 0.0084 ... I'm leaving it there. I'm keeping it in my calculator. Okay, I'm going to write that down just so I know generally what we're doing, but keeping that number in my calculator, and I'm then going to do 0.0084 and all the other numbers in my calculator, and I'm going to times it by the amount of energy in kilojoules they've given me, which is 88.1. And that is going to give me this answer of 0.7403363134. It's a huge long answer, but again, we've circled the 3 significant figures because that's the essential bit. So our 3 significant figures is 0.740. Okay, so again, drawing that line, making sure that we've done that rounding correctly. 2.5. What type of reaction takes place when hydrated cobalt chloride is heated? Well, that very first thing we talked about, endothermic, okay? I've just said it's endothermic because I've realized that energy is being taken in, so I can say endothermic. But actually, right at the beginning of this question, I wrote down something. I knew that copper sulfate underwent a reaction called thermal decomposition, and I realized it was the same sort of reaction, so I could also write thermal decomposition. Okay, both are correct, and actually the question gives you enough clues to be able to do both of those. This question is about life cycle assessments. Now for me, I see life cycle assessments and I think there are 4 stages to this. The first stage is the raw materials. How do we get them? And again, how much energy? Okay. Second stage is going to be the manufacturing. We're going to get those raw materials and we're going to make them into something. Second stage, or third stage I should say, is use, potentially reuse. And the fourth stage is disposal. Okay, and all of those are all going to be about energy. Okay, now that's everything about life cycle assessment is to do with that. And then it says this beautiful table with lots of things in it, and then at the bottom it says evaluate. Now that is the command word, the most important command word to see. It says evaluate the use of glass for milk bottles compared with the use of a polymer for milk bottles. Use features of LCAs in your answer, and crucially, it's got it in bold. It says use table 2. That means if you don't use table 2, you will not get all the marks. And if you do not evaluate, you will not get all the marks. Evaluate means you have to give a justified conclusion or some sort of judgment. Okay, now you can look through the whole thing. I always say the best way I say it is give your judgment first. Look through, decide, do you think glass is better or do you think polymer is better? Don't just make it up on the spot. Look through the table first. So we can look through the table and we can say these 2 things. Well, I can say glass, well, all of those things are renewable, but crude oil is not. So I can say crude oil is finite. Okay, and then I can look at this and then I can say, well, glass, and I'm going to abbreviate because this isn't really my answer, this is just going to help me with it. Glass needs more energy. Okay, I'm summarizing each of these rows. Well, need to manufacture. Well, I've got my raw materials, that's step one, and then glass needs more energy for manufacturing as well. I then look at this. Oh, glass is heavier. Well, how does that to do with energy? Well, it might not be to do with energy. It might be to do with transport. So, costs more to transport, or more energy to transport. That's where energy comes in. It's more energy to transport. Last one, glass used more times. Okay, it's not that everything's negative or everything's positive. It's always going to be a mixture. Okay, and then we have both can be recycled. Again, all I've done is gone through this table and had a look. Then if I look at this table, I can say, do you know what, actually, I think polymer's better, because glass needs more energy to extract, and in manufacturing, and it's heavier. That might not be necessarily make it the best one. So I'm going to say a polymer is the best to use for milk bottle. Okay, that is my statement. That is my judgment. Everything I say after that is going to back up this point potentially. If I don't write this judgment though, I am never going to be able to get 6 marks. I can't get more than 3 or 4 marks because I have to have that judgment to be able to get 5 or 6 marks. I then can list it. Well, actually, I've pretty much listed it. All of this can be in my answer. I can then say, well, crude oil is finite, but glass raw materials are not. Glass needs more energy to extract, but polymer does not. Glass needs more energy to manufacture. Polymer is less. Now it says use table 2. We are using table 2, so we could use numbers here. We could say 6750. We could say 750. We can use these numbers. We can say 200. And we can say glass is used more times. And we can say glass is used more times. That's still using the table. And we can say both are being recycled. It can be in bullet points. It doesn't have to be a massive paragraph. But you need to use each of those points linked to all of those, the raw materials, the manufacturing, the use, and the disposal. That's why knowing those 4 steps for an LCA is so important. Milk is also sold in cardboard cartons. Now this is a separate point, totally different question almost. Carton is used, it says use the equation. So you got to use the equation. There are 3 parts to the equation, which means for a relatively simple one, they're going to give you most of the information, okay? And they've given you density. So if you write 0.40 equals, it says we need to calculate the mass, that means we don't have it, mass divided by 40. Okay, now we need to then solve for mass. So we're going to do 0.40, so that's not an equals, that's an arrow, times by 40 equals mass. That's how we write it, because that's what we're going to do in our calculator. And we end up being the mass is 16 grams. This question is about the fractions obtained from crude oil. Now there is a lot of information we need to know about crude oil, but we need to be thinking, is it fractional distillation? And then the very first line, crude oil is separated by fractional distillation. Now we should know what fractional distillation is and be able to describe it. So if we look, the fractions obtained include lubricating oil, naphtha, petroleum gases, and then it says, it gives us this table of results, okay? We don't have to have memorized this, which is why they're giving it to us. Explain how these fractions are obtained, which means, explain means we need to say how they're obtained and why. So what is causing that? By fractional distillation, and we've got 4 marks. This is our opportunity to say, what is fractional distillation? Well, we can say crude oil is heated until it vaporizes until it turns into a gas or vaporizes. Okay, so that's part of it. We heat crude oil until it turns into a gas. Why is that important? Now if we think, we then have our fractions. Okay, we've heated our oil until it's a gas, And then we can think this is our fractional distillation column, and we can think as it goes down, it's bigger, or bigger molecules, but also it's hotter at the bottom. Okay, so we can say it's hotter at the bottom, and obviously we can also say cooler at the top, which is basically sort of saying both sides, just to make sure that they know we're saying cooler at the top as well. Okay, now what's the next step? Well, this gas is gonna condense, and this is the other important bit. We've heated it until it evaporates into a gas, and then the gas is going to condense into a liquid, and this is where it's important. All those key terms, not just condense. Tell me what condense means. Condenses into a liquid. Okay. Well, why does lubricating oil separate differently to naphtha? And that is because this is our explanation. The gas condenses into a liquid, but at different boiling points. So we can now use these specific examples. We can use petroleum gases, not at the top rather, but nearer the top. And we can say lubricating oil nearer the bottom. So our explanation is that arrow at different boiling points. It's all about the boiling points, and if we look at the table, it's talking about boiling points. Fractions from crude oil can be processed to produce livestock for the petrochemical industry. Now, this is a different word. We haven't used petrochemical very often, but which two are useful materials? Now, I've circled two twice because it's quite important. They've put both in bold. Okay. Now, if we think of alloys are metals. That's sort of paper one. So it's not going to be that one because it's not about crude oil. Ceramics tends to be about our sand or our clay, so it's not going to be ceramics. Okay, detergents. Well, detergents we mean by a lot of things, and actually a lot of the detergents we use are crude oil, so it is detergents. Fertilizers, that is a lot of our industry, but it's not petrochemical, it's more of our organic chemistry, so it's not fertilizers, which means it has to be solvents. So it's important to realize fertilizers is the organic, and again, more from a separate chemistry, the triple science rather than from a combined. And you should know that. You should know fertilizers are the higher level of organic because we're talking about ammonia. And ammonia is not to do with the petrochemical industry. And whereas ceramics, it's the detergents and the solvents. Okay, next question. Another fraction is obtained from crude oil is petrol. Now, we should know some uses of petrol as well, so we can say the uses, the properties, those might come in handy. And then it says complete the equation for the complete combustion. Okay, both of those words are important. Complete combustion means it's going to be oxygen. So we already know that that's going to be oxygen. O2, remember it's a diatomic molecule. And then combustion, we know it's going to be only carbon dioxide and water because it's complete. So we can write those in straight away. Those are the chemical formulae, but it also says you should balance the equation. Now the way we start from balancing equations, we look at the most complicated, which is our C9H20, and we go through each individual element and try and balance that first. So our C9, we obviously have 9 carbons on this side. We've only got 1, so if we do a big 9 there, that balances out our carbons. Okay, that's where we get the 9 from. We then look at our hydrogens. We have 20 on this side, and we only have 2. So if we put a 10 here, that gives us our 20 hydrogens. That's where we get that from. And then all we've got to do is how many oxygen do we need? Well, if we count our carbon dioxide oxygens, that's 18. Plus another 10 from our water, that's 28. We've got 2 on this side already, so 28 divided by 2 is 14 oxygens. Okay, so we can get rid of those arrows just so they don't confuse you. So our final balance symbol equation looks like that. Petrol obtained from crude oil contains sulfur impurities. Okay, now we talk about sulfur in this topic, and we only talk about it really as sulfur dioxide and the problems with sulfur dioxide. Okay, so explain why sulfur impurities are removed before petrol is burned in car engines. Oh, that's exactly that. Well, sulfur produces sulfur dioxide, which is what we said. As soon as we get to sulfur, we know we're going to be talking about sulfur dioxide. That's our first point. And then, so what? Well, we have to know about the problems. That's the other bit we need to know about it. And it causes acid rain. We could put breathing problems as well. Acid rain is more of an obvious one. Then table 4. This is our information. Range of number of carbon atoms in each molecule. Okay, it's a lot of information, or rather it's a big sentence really, phrase. I tend to simplify it to molecular size, or size of the molecules. Okay, this is smaller, and this is bigger, or larger. Okay, and that's important. We have a table for a reason. We can annotate the side of the table to help ourselves. A student predicted that heavy fuel oil is more viscous than kerosene. The student's prediction was correct. More viscous, right? What does more viscous mean? More viscous means thicker. Justify the student's prediction. Okay, now why? Justify is essentially saying, why is it thicker? Well, we've labeled or annotated our table, and that's going to really help us, because we can see that we can label it even more bigger. We can also say is thicker as well. Now, if the bigger one is thicker, that means the smaller one is probably going to be thinner. And what else is changing? What's the molecular size? That's our smaller and bigger. So we can set, then that's really what we need to say. So we can say heavy fuel oil is larger, and again we're going to use this phrase, molecular size, and is more viscous. Well, what do we notice as we go up the table? You could go down as well, is the smaller the molecule, the less viscous, or the lower the viscosity. Okay, we then have heavy fuel oil fraction can be processed to produce smaller hydrocarbon molecules. Well, smaller, I know what that's called. That's called cracking. Okay, that's that breaking apart of large molecules. Then it says name the process which produces smaller molecules. Well, I know that already. That's cracking. I've just said it. Okay, that's where linking those, we're making it smaller. That's what we call cracking. And give the conditions used. There aren't many times we have to give conditions, but it's this is the time. So what do we need to do for cracking? It's a catalyst. This links to our rates of reaction topic. Catalyst is used to speed up the rate of reaction, and it's going to do this for cracking. That's one, and the other one is a high temperature. It's not just a bit hot, okay, it's a high temperature. In reality, it can be anywhere between 300 and 900 degrees. I think they will allow that as a temperature option, okay. Hydrocarbon molecules containing 7 and 8 carbon atoms can be produced when heavy fuel oil is processed, and that's our cracking. Which pair of hydrocarbon molecules would both, again, both is important, turn bromine water colorless? Now this is really important. This is another test you need to know. Bromine water only turns colorless with an alkene. And how do I know it's an alkene? Well, it's CnH2n. And we could talk about unsaturated, double bonds, everything like that. Well, I've got these formulae. All I need to work out is which ones follow that rule. Okay, so I start at the top. C7H14, that works. C8H16, well, that works. I can look through the rest just in case. Well, C714 works, but 18 doesn't, and 716, that doesn't work, and 716 and 18, that doesn't work. So it has to be that very first one. This question is about water. Sewage is wastewater. Now straight away, if I look at wastewater, there's a certain sort of method, these 4 steps I'm going to need to talk about. I know that wastewater, we're going to be talking about filtering something, we're going to be talking about sedimenting something, or sedimentation, okay? And then we have these 2 other steps where we deal with the remnant, because we have the sludge and the effluent, okay? So I would talk about the anaerobic and the aerobic digestion. And I know it's going to be those 4 things because that's what we do when we talk about wastewater. And in actual fact, for our wastewater, that's what we're dealing with, okay? If we then look at the question, describe how sewage is treated to remove organic matter. Well, organic matter comes into all of that. So all I've got to do is get those 4 things, put it in here, but as full sentences, and say, so we're going to filter to remove the solids. Not just filter, we need to say what we're filtering. To remove the solid particles, okay, solid matter I should say, and then we're going to sedimentation, but it's not just sedimentation, but we're going to say what we're going to make, to separate into, and we have our 2 things, our sludge and effluent. So the sludge is the solid, the effluent is the liquid of sorts, or solution I suppose. The sludge we then do anaerobic digestion. Remember that's without oxygen, or with a lot less oxygen. Anaerobic digestion of sludge, that removes the solid, and aerobic digestion, again that's the oxygen or more oxygen of our effluent, just to make sure we've got rid of everything inside. It's a bigger question because it's got this table. Seawater and groundwater are treated to make them potable. Now I see the word potable and think there's certain methods of making it potable. We're going to be talking about sterilized, we're going to be talking about reverse osmosis if we're talking about seawater, which it says we are, so we might be talking about reverse osmosis, okay? Now if we look to the question, seawater is desalinated. Desalinated means to unsalt something, so we're removing the salt from the seawater, and that's during process 1. So this reverse osmosis is our desalination. We are removing the salt, and that's where it's really important. We're going to remove salt. And obviously our salt, if we think, is NaCl, sodium chloride. Which pair of concentrations could represent X in table 5? Well, if we know that desalination is removing salt, that means these numbers of 0.5 and 0.5 are going to get lower because we're going to be removing some of it. So if we look and we look to the top, both of those numbers have got lower, so we might think it's that, and we're just going to check. Well, the second one, chloride hasn't got lower, so it cannot be that one. The third one, sodium hasn't got lower, so it cannot be that one, and the fourth one, they haven't changed at all, so it cannot be that one either, okay? And then explain why, so we need to be saying something and then why. Why do the concentration of sodium ions and chloride ions in the groundwater, or rather in table 5, why are they unchanged? Well, again, they've put in bold process 1 so that we look here at process 1, which is filtration. What does filtration do? It removes solids. And they're asking, why are they unchanged? Well, if they're ions, the ions are dissolved in the water. The ions are dissolved in the water. It's a solution. We know that when ions are dissolved in solution, filtration doesn't work. Why not? Because the ions pass straight through the filter paper, straight through the filter. The filtration, we've already mentioned on the previous question, filtration only removes solids. So this doesn't work for this case. Okay, explain why the groundwater in table 5 requires process 2 before the water is safe to drink. Now, process 2, again, if we look at the table, process 2 is about sterilization. Okay, now sterilization is about killing anything or destroying any organisms, microorganisms that are inside that might cause damage to humans or animals, really. So all it's saying is explain why we sterilize things. Well, we could say the water contains harmful microbes or microorganisms, and that's a big part of it. And then, so what? Well, if water contains harmful microbes, sterilization destroys them. Okay, so it's relatively simple as long as we know what sterilization is, and that's what process 2 is. Now, after treatment, the groundwater in table 5 is sold by a company as pure water. The groundwater is not chemically pure because the water contains sodium ions and chloride ions. Suggest what the company means by pure. Now, this is that little bit, and again, they've put it in inverted commas, pure, because it's important you realize that doesn't mean pure. We have chemistry pure, which is H2O, and we have company pure, which is not H2O. It means we haven't added anything to it. Okay, so we can quite literally say nothing has been added to it, has been added to that water. That's what a company can say pure. Okay, now chlorine is used to treat some of the groundwater. Back to our sterilization. Describe the test for chlorine gas. Give the result of the test. It's always set out like this, so the test bit has to be perfect, and it has to be damp litmus paper. Cannot just be litmus paper, okay? And the result, I always say it bleaches white. Because we know about bleaching for clothes. If we bleach something, it accidentally goes white, or bleach our hair, it goes white. Okay, this question is about the chemistry of the Earth's atmosphere. We need to be thinking oxygen, nitrogen, carbon dioxide. Those are the big three. And then if we go all the way down to the question, we've got this graph where it says A, B, and C, and they're highlighted. So we're probably going to be talking about those areas. And then it says, explain the change in the percentage of gas labelled A. Well, we need to look at what that dotted line is. And it's explain, which means we have to say what we see and then why. Well, we can say nitrogen increased. That's our simple description. Nitrogen increased. Now, why did nitrogen increase? Because volcanoes were erupting. Okay, we then have explain the change in percentage of gas in the region labelled B. So again, we've done A, now we're going to do B. We can say again, carbon dioxide is decreasing or decreased. Now, why did it decrease? We've got to be very careful because at this point, 2,500 million years ago, that's when oxygen started to appear in the atmosphere. And which means that's when plants started to appear. So we can't talk about photosynthesis yet. We have to talk about where it's going first. So we have to say carbon dioxide decreased because it dissolved in the sea, or in the seas. Now the next question, compare the changes in the percentage of gases in the region labelled C. So we've done A, we've done B, now we're doing C. Well, again, we say what happens. So we can say CO2 decreased, and we can say oxygen increased because that's what we can see. And now we need to say how this comparison part. Well, obviously one is increasing and decreasing, but if we look at the gradient of both of them, they're very similar. One is a positive gradient, one is a negative gradient, but the slope itself, the steepness of the slope is very similar. So we can say they increase at similar rates. Now, if you want to go, you can actually calculate that, draw a tangent on the line and calculate the rate exactly where they cross to see if that's true, but they are at similar rates. Now, 6.4, what process causes the changes? Again, so we've talked about C, but now we're talking about why. What process is happening? Well, oxygen is appearing. We're talking about oxygen, which means we're going to be talking about photosynthesis. Natural gas is a fossil fuel. Describe how natural gas or deposits of natural gas are formed. So we're doing our description. And there are 4 points to this. Even though there's 3 marks, there are 4 points to this. Because we have plankton die. When the plankton died, they sank to the bottom of the sea and they were covered by sediment. And once they were covered by sediment, they had high temperature and pressure placed upon them. But it wasn't for 10 seconds. It wasn't for 10 years even. It was over millions of years. And that's what's important. It's the millions of years. Even though there's only 3 marks, you need to be saying all of those things. Ammonia is produced in the Haber process. Now, straight away, that's given us such a massive hint. Haber process, ammonia. We're going to be talking about equilibrium, dynamic equilibrium, Le Chatelier, all of these factors. And then it's getting that into your head that you're remembering all those things. The raw materials are nitrogen and hydrogen. The equation, well, obviously we're not going to have a balanced equation because we've got that already, but it's important to note they've given us the state symbols. They're all gases, and that's important to realize that we're starting, our reactants are gases, but our product is also a gas. And it says give the sources of nitrogen and of the hydrogen used in the Haber process. Now this is important. It's just one of those things you have to know. Okay, nitrogen, well, we know nitrogen comes from the air, and hydrogen is not just methane. Okay, it can be also natural gas. If we go back to our fractional distillation of crude oil, methane is one of those natural gases that we get at the top of the fractionating column. Question 7.2. How does the equation for the reaction show that the atom economy of the forward reaction is 100%? Well, 100% would be the products, and this is our atom economy, products over reactants times by 100 equals 100%. That's what this question is asking us, okay? The number of atoms of our products, and it's not just of our product, it's of our wanted product, over the total number of atoms of our reactants, and we only have one product, so it has to be correct. There's only one product, or one product only, so it has to be that. Our next one, figure 4 represents the Haber process. We have a reactor with unreacted and we have X, which means straight away we know we're going to be talking about X. Now it's important to look back and note when we look at that reaction or the equation that they're all gases, because now when we have nitrogen, hydrogen and ammonia coming from the reactor, we know that they are all gases, and now that they are a mixture of gases. So when it says explain how the ammonia produced is separated, we know we're going to be separating a mixture of gases. Okay, well, how do we separate a mixture of gas? That goes back to our fractional distillation. We have to cool them down. And what happens? Well, the gases will condense at different boiling points, because we know that. That's from our fractional distillation. And crucially, how do we know that ammonia is going out at the bottom? Well, ammonia turns into a liquid. We know ammonia turns into a liquid because ammonia is being collected, and the other unreacted nitrogen and hydrogen are going back into the reactor as gases. So it's useful to label this diagram. We know that nitrogen going in is a gas. We know that hydrogen going in is a gas. We know that the unreacted nitrogen and hydrogen are gases, which means this at the bottom, after we've cooled and condensed it to separate it, our ammonia is a liquid. Okay, the first 2 points have been plotted. You should. It's really important we see this bit, okay, because this is going to be our checklist for how to get marks. First one, use a suitable scale for the x-axis. Well, they've plotted one. That first cross is the 60 and the 9, which means that first line must be 50. And the next one must be 100, the next one 150, the next one 200, so forth, all the way until we get to the end. Now it's all well and good saying, oh, I know what it is, I'm just gonna plot them correctly but not write it. Well, you have to write these numbers or you're not gonna get the mark for using a suitable scale. Then plot the remaining data. Okay, so we now have 60, they've plotted, 120, they've plotted, 180 is our first one that we have to plot, and it's going to be at 180 at 25. And we can tick them off as we go. It's not a problem to use your table like this. We then go to 240, and that's going to be 31. You can notice even with this pen, the crosses are going to be quite small on the dot, because if they're more than half a square out, it's not going to count. We then have 300 as 36, and then we have 360 is 40, and then we have 420 is 43. Okay, those are all our points. Right, we plotted the data. It's going back to this checklist of things. We now need to draw a line of best fit. Well, I'm going to start at 0, and I'm going to do this. Okay, it goes through pretty much every point. Not exactly, but it's showing generally what's happening. Okay, I've drawn a line of best fit. Done. I've done 7.4. I'm going to get my 4 marks. Now 7.5 at the bottom. Determine the percentage yield of ammonia at 450 degrees at 500 atmospheres. Well, show you're working on figure 5. So I can't just pick a random number. I have to show my working. So how am I going to do this? Well, at 450, oh no, not at 450, sorry, even I read it wrong. It's 450 degrees C, and this is in atmospheres. So I'm actually looking at the 500 atmospheres. I'm going to draw my beautiful straight line up to the top. And then I'm going to draw my line across. And I'm going to work out the percentage yield as being about 48%. Okay? That's all I've done. Literally drawing those lines shows my working out of how I found that number. The equation for the production of ammonia in the Haber process is the forward reaction is exothermic, and they're giving us the conditions for this exothermic reaction. Now, for all of these, I'm saying, right, exothermic, that's going to be important because it's about equilibrium. We've got temperature, pressure, presence of an ion catalyst, so we've got all those parts now. Explain why these conditions are used. Okay, so straight away, I'm boxing this off, and I'm, again, going to use it as a tick list, and when I talk about it, I'll tick it off, so I know I'm going to be using it. For the economical production, economics, for me, I'm going to be talking about energy, and I'm going to be talking about cost. So it's actually a plus. I'm going to be talking about energy and cost for the economical side of it. You should include reference to the rate of reaction and the position of equilibrium. That's what I need to do. That's my sort of 6 marks essentially. So I'm going to talk about rate here. I'm going to talk about equilibrium here. And I'm going to talk about it as a table essentially. And I'm going to tick off as I talk about the conditions. So I can say, well, higher temperature, how does that affect the rate? Well, particles have more energy. They have more energy. If they have more energy, they have more frequent collisions. Okay, that's my rate side for higher temperature. I can then do my higher pressure. Now, why am I using the word higher? Because essentially, I'm comparing, I'm saying, why is it this? I can say a temperature of 450, which means that as well. Okay, so a higher pressure also means not more energy this time, but it does mean more frequent collisions. And then we have finally catalyst. I'm sort of ticking it off. I've done temperature, I've done pressure, I've done catalyst. Now I'm going to do catalyst. What does a catalyst do? It lowers the activation energy. Okay, I can do all three of those for rate, and now I'm going to do the same for equilibrium. So how does a higher temperature affect my equilibrium? Well, if it's a higher temperature, I go back to temperature. Oh, I've got exothermic here. The forward reaction is exothermic. Therefore, if I increase the temperature, the equilibrium shifts to the left. Equilibrium is going to shift to the left. Why? Because it's an endothermic reaction, is the backwards reaction. Okay, and then we have higher pressure. What happens if there's higher pressure? Well, this again, I'm counting my molecules. The equilibrium this time shifts to the right. And remember, it's an explain question. I'm not just saying shift to the right, I'm saying why that is. And there are more molecules on the left. So I'm saying why that is. Just like with the rate, I said there's more energy, which causes the more frequent collisions. I'm saying the equilibrium is shifting to the right because there's more molecules on the left. And then we have finally one, how does a catalyst affect the equilibrium? Well, it actually has no effect whatsoever. But it's useful to write that as well. Okay, so those are my rate of reaction talked about, my equilibrium talked about. I haven't done, and this is where circling that economical and saying what it's about helps. Because you think, I haven't talked about that yet. I've talked about these twice now. I now need to talk about the energy. Well, I can say higher temperature and higher pressure. So they're both the same in this sense. They require more energy, or lots of energy to work to sort of increase the temperature. More energy means more cost. Okay. However, a catalyst, and again, if you notice, I'm just going through these three conditions every single time. A catalyst, well, actually, that lowers the cost. Okay. It lowers the energy cost, definitely, because in theory, I should keep it cooler. It doesn't need to be as high pressure or as high temperature, for the rate at least. And then our last bit is, so what? Well, this is the compromise. It is a compromise between the rate and the yield. Now, yield is a word they have not used in this question at all. You've got to link everything to do with the yield, and that's why your equilibrium really helps. Your rate, your yield, and the cost. And just by saying it's a compromise between those things, you've talked about cost, you've talked about rate. The equilibrium is to do with the yield. You've answered this question. 6 marks. This question is about the reaction between sodium thiosulfate and hydrochloric acid. Now, you in your head should be thinking, this is a required practical. So we need to know generally what's going to happen here. And then it says, when hydrochloric acid is added to sodium thiosulfate, the mixture gradually becomes cloudy. And they've given us the equation. It's always important to look at the states. Aqueous means you're talking about solutions. Aqueous solution, liquid water, gas sulfur dioxide, and solid sulfur. Okay, sulfur is produced in the reaction. Right, straight away. Why does the mixture become cloudy? Well, why is it? Because sulfur is a solid. Okay, if we have a solid in the mixture, then it's going to be cloudy. Figure 7 shows the results. So we have this whole thing here with a long method, but we don't even have a question yet. Okay. Percentage of light reaching the light sensor decreases. Determine the rate of reaction at 30 seconds, and you should draw a tangent. Now that's the important bit. It's telling you to draw a tangent. Okay, so if we draw a tangent, it's going to go exactly through 30 centimeters. And we're going to draw a beautiful triangle to make sure it's there. And yours is going to be with a ruler, so it's going to be even straighter than this one. And then we need to write these values so we can know what to do with them. Now I've got 12 here and I've got 58 here. Okay, if you calculate it, it might not be exactly the same for you. That's not a problem, don't worry, as long as it touches at 30 seconds. Now, we then have 60 take away 20, because that's our y-axis, divided by 58 take away 12. Well, that's the same thing as saying 40 over 46. Okay, and that is going to equal 0.8695. I'm doing the dot 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 because you're keeping it in your calculator. Okay, now this is our ratio of percentage of light to time in seconds. We have, however, we know that 1% is 7.1 times 10 to the minus 5 moles. So we need to know how many moles this is going to be, because this isn't how many moles, this is the percentage. So we need to do 0.8695, again using our full number in our calculator, and we're going to times that by 7.1 times 10 to the minus 5, and that is going to equal our rate, which is 6.17 times 10 to the minus 5 moles. Okay, now you get lots of marks for that. Marks for just calculating or drawing a tangent correctly, a mark for writing this calculation, change in y over change in x correctly, a mark for calculating that ratio, then timesing it by 7.1, and also the final answer, the rate. It then says explain why the rate of reaction changes between 0 and 60 seconds, answer in terms of concentration, and again it says use figure 7. It's an explain, which means we need to describe what is happening first. So we need to say straight away the rate is decreasing. Now we can say why. Why is the rate decreasing? Well, the rate's decreasing, and the rate always decreases initially because the concentration of the reactants decreases. That is why our rate is decreasing, because we're using up the reactants in the reaction itself. Now, figure 8 is a repeat of figure 7, and figure 8 shows the results of 0.10. Now, I'm circling the number this time because it is important to circle the numbers. It's going to probably help us later on. And it says sodium thiosulfate was in excess. Now, that's really important. Excess means too much. Okay? The line of best fit on figure 8 is horizontal between 80 and 100 seconds because the reaction stopped. How did we know the reaction stopped? Well, you might think the reactants are used up, except for the fact that they've said in excess, which means we've got too much of that. So the sodium thiosulfate wasn't used up. The acid was. The hydrochloric acid was used up. We still had some sodium thiosulfate there. It hadn't used it up, and they told us that by excess. And that's where it's important to look for that word excess and always think too much of that. We haven't used it all up. Okay, now we circle this other bit, this 0.10. Well, 8.5. Sketch a line on figure 8 to show the results you would predict for 0.2. Well, it's important to have that because you can say, well, which is a bigger concentration or a larger concentration? That's the one they've asked us for, the 0.20. Now, if there's a larger concentration, that means the rate of reaction is going to be faster, because as we increase the concentration, the rate increases, which means the gradient of our line is going to be steeper. It does not say we have more of it, so all they're looking for, they always ask this question, is they're looking for a steeper line which is slightly less wobbly than that, a steeper gradient which levels out at exactly the same. So it needs to level out at 24 and it needs to be steeper here. It can be as steep as you like it to be. It doesn't really matter. They are looking for a line on this side, the steeper side, and it has to level off at exactly 24 again. The same student did the investigation again the next day. How could the student improve the method so that the same percentages of light reach the light sensor? So we're looking for these errors along the way. Well, if we make sure the same amount of light, the same percentage of light, is that going to change if we record it differently? Well, no, it's not. Now, it is going to change the percentage of light if we are stopping light from other sources. So it has to be that one. Is the percentage of light reaching the light sensor going to change thiosulfate? No. Or even using a more sensitive light sensor. So it has to be stopping outside light. A little bit like your photosynthesis practical in biology from a heat point of view. The student improved the method so that similar results were obtained on different days. What name is given to similar results obtained on different days under the same conditions by the same student? So there's a lot of same. I'm looking for same student really, because anomalous is about there being different results, so we don't want that. Precise is the equipment we're using. And then we have an option between repeatable and reproducible, and that's why the same student is important. Repeatable is the same student, and reproducible is a different student, or someone else. Which expression represents the relationship between the volume of sodium thiosulfate solution used and the mass of sulfur dioxide? Well, we can see the graph here. As the volume increases, the mass of sulfur increases, and we can actually see that it is directly proportional, because at 50 centimeters cubed for thiosulfate it's 0.15, and at 100 it's 0.3, so it has to be directly proportional, which is this top one. Then it says determine the simplest whole number ratio of the volumes. Okay, this is one of those sort of mathsy questions where we can choose whichever number we want. Well, I've chosen 0.25 for the mass, and I've chosen 0.25. Okay, the mass has to be the same. Has to be the same mass. Okay, which means if I go down and look here, that number is going to be 80 for my thiosulfate. So I can almost sort of say thio to acid, and that's going to be 80. And if we look over here, that's going to be about 315 actually. Okay, now 315, well, I'll rewrite it over here actually so it's easier. We've got a bit more space, so I'm going to do 80 and 315. Well, I need the simplest whole number ratio of 80 to 315. So I could work that out. The way I would do that is I would do 80 divided by 315, and I would work out that 0.25 to 1 is my ratio, and therefore the simplest ratio is going to be 1 to 4.